Now, next thing, I will look at the scalar product in 4 dimensions. So we said that B dot A is the same all inertial frames. Now we have the tool, so how I can write this in terms of the Einstein summation rule. So that is very simple. Put one indexes down, put the other indexes up. So contravariant and covariant, or you can say that B mu, let's say A mu, they are the same. So if you see that the one up and down, that means that there's a summation or contraction, okay? So if you go to the different inertial frame, and if you want to write again what is going on this scalar product, that is simple. B is down, covariant. So start with some index and left with alpha index as a free. So beta and beta will be sum up and left with alpha. This is the covariant transformation, del x beta over del x prime alpha. And here index is up. Say another gamma, make a contravariant transformation, del x prime over del x. What is the summation index? Gamma. What is the free index? Alpha. So basically, the structure is the following. Gamma and gamma is contracted or sum, 0, 1, 2, 3. Beta and beta is sum or contracted, 0, 1, 2, 3. And that is what are the leftovers? Alpha and alpha and alpha and alpha. So if you look at this B prime scalar product with A prime, what you are going to see, this x prime alpha and x prime alpha will be cancelled out, and you are left with del x beta, del x gamma, B beta, A gamma. And you know one thing, maybe you don't know, if beta and gamma different from each other, that is 0. If they are the same contravariant coordinates, they are 0, 1, if they are same, otherwise 0. So you can express this as a chronicle delta, beta and gamma, and here you have beta, beta is down, A of gamma is up. So when you do some calculation, whatever, if you see that the same index in the same place, that means there's something wrong. So this is down, up, it's good. This is down, up, good. But if it were is down, that means that your calculation is incorrect somewhere. So basically, you have two options here. Either you can contract this beta and beta, left this as a gamma, or vice versa, contract gamma and gamma, left it as a beta, whatever you choose. So if you sum up beta and beta, that will turns to be beta B gamma, A gamma, and that is nothing but B dot A. So B prime dot A scalar product in 4 dimensions is the same in all coordinates. So this is the mathematical presentation of this. So once we did a contravariant transformation and we did a covariant transformation, and we find that the scalar product is the same in both coordinate systems. So if you have somehow you have this kind of structure, that means that something wrong. Okay, look at the calculation again. So what is the next? Next, we will define the metric tensor, and we will learn how to lower the indices down or up. So contravariant to covariant or vice versa. So I am erasing this part. So what we said earlier, the Planck element, invariant Planck element, could be written as dx0 square minus dx1 square dx2 square dx3 square. Is it right? Yes. So we can write this using a different tool. We can introduce a tensor such that g alpha beta and let's say dx alpha dx beta, and try to find the above. Can we do? Yes, we can do. If we say that if this is 0 and this is 0, that means that dx 0, then what should be g0, g0, 0? 1. If it is 0, if it is 1, what should be g0, 1? 0. So if it is 1 and if it is 1, that is dx1 square, g11 should be minus 1. Okay. So this is the construction of the metric tensor for this kind of Planck element. So the elements is g0, 0 is 1, and all other 1, 1, 2, 2, 3, 3, minus 1. And basically this is in the following form: 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, minus 1, 0, 0, 0, minus 1. So off diagonal elements is 0. So this is called flat space-time metric tensor or metric. So that is called as a flat space-time. Why they call flat? We have to go to general relativity and make a test whether this 4-dimensional space and time has a curvature or not. Okay, so this is in 4 dimensions, it's flat, but for the testing, we have to go to the general relativity and to look at the curvature and see that it's flat. There are other metric tensors, which at least I am familiar in the research. For example, Relativistic, probably you see that. It is the gravitational effect, and they are more complicated forms. The Kerr metric is the rotating for the black hole, rotating black hole, space and time drags in that case. And what I know is other is the Friedman-Robertson, no, Robertson and Walker matrix. So that is the expansion for the universe. That's the difference. So there are several metrics, and in astrophysics, the Schwarzschild and Kerr metric is used. In cosmology, Robertson and Walker is used, but I don't know for the mathematical physics. So they have lots of metrics. But so far that's easy. So we have the rule. What are the properties of the this metric tensor? One of them, you see that if you interchange alpha and beta, nothing change. And the other is covariant and contravariant forms are the same. G alpha beta is equal to G alpha beta. That is the other thing. So index up or down, they are the same. And the other thing, if you contract the G alpha gamma with G gamma beta, what we are going to obtain? If you contract this middle with gamma, you will obtain the definition of the chronicle delta when alpha and beta equal to each other 1, otherwise 0. 1 when alpha is equal to beta, 0 when alpha is not equal to beta. These are the simple rules for the metric tensor, but main job of the metric tensor is the following. You can make the contravariant to the covariant, covariant to the contravariant. This is an important job. So basically, in this place, let me show the following. If you have a index is up, what is this? Contravariant vector. Act the metric tensor, contract with beta, that will lower the index. Look at the free index. Beta is some, free index is alpha, that is low. So basically, what is going on here? You are lowering the index from up to down, contravariant to covariant. And what is changed actually if you act this one? So how let's say that x0 is the what? Time coordinate, for example. If you act this to the first one, what is this? So what you are going to obtain? Let's say this is 0. This is 0. This will be 0, 1, 2, 3. If you do this, the time coordinate doesn't affect it. But if you look at the other one, let's say this is 1. This is 1. 0, 1, 0. 1, 1, 1, 1 is what? What is the 1, 1? Minus 1. So what happens? This goes to negative its value. If you continue, that will continue. So basically, acting the metric tensor to the vector change the sign of the space from plus to minus, minus to plus. In different conventions, they use the same metric tensor, but the convention is the following. Instead of writing 3 minus sign, they write 1 minus sign, they use this as a plus. Okay, I am following your book. So the vice versa of this, so you can have a covariant and vector, and you can act the metric tensor. You can make these indexes up. Again, we have to look at all the times the summation index and free index. Okay, summation index and free index. Generally, if the A alpha, you can denote this as a time coordinate and plus a space coordinate. If you act a metric tensor, if you lower the index down, so let us put a process here. So this is not a good place, maybe this one. So act the metric tensor like a processing and lower this. What will be change? This will go to the minus. Space part will be reflected. If you have a higher rank, you can use the metric tensor for lowering and uppering the indices. So one particular example is what? So we can say the following. Let's say we have F. We have indices here. Let's say 1, 2, 3, and beta, and here. Like this is what 1, 2, 3, 4, 5 rank, higher order. If you want to make this index upper, all you have to do, act to the metric tensor, alpha, beta, make this index upper, and you will obtain what? F, 1, 2, 3, down. These are the sum indices there. But beta and beta is sum, and the index is up alpha, and here it is down again. Okay? So say that many indices here, 5 indices, and this will, if you act this the metric tensor, this will make this index up. Means that the contravariant. And again, you can define the scalar product very easily. B dot A, again, go to the scalar product. Say B alpha, A alpha. What is the form of the 4 vector when the index is done? That is B0. This is B0. And minus B, and that is A0 plus A. If you look at this scalar product, what you are going to obtain? B0, A0, what? Minus BA, B dot A. If you do the opposite, you will get the same thing. So if you make this upper and lower, this will be positive, this will be negative, you will get the same thing. So we have one tool for the metric tensor, and in order to study that the covariant form of the electrodynamics, we will have to know the derivatives. Okay, now let us define that the derivative. And this is the, again, very important point, and it helps us, you will see that it will help us too much to defining the covariant form of the electrodynamics, Maxwell's equations, gauges, and so on. Now, if you have a derivative operator, partial derivative in 4 dimensions, how you can make the transformation to the different coordinate system. How you can do? You have one option, similar to the chain rule. So what is that option? Sum up this with beta, left with free as the alpha. So do you agree? But there's a very tricky point and nice point here. What kind of transformation is a covariant or contravariant as a format? Covariant. But what is the form of this component? Is it covariant or contravariant? This little component. Index is up. Contravariant. So this is transformed as what? Covariant form because of it looks like this structure. So basically, if we defined let me write here covariant again. If you want to define this derivative operator, since in 4 dimensions, since it is similar to the form of the covariant, you have to we can put a notation to where index down or up. Down, because this process or pattern is similar to the covariant process transformation. Okay? This is very important. We can express this as a del prime alpha, or in general, del alpha is equivalent to what? Del of del x alpha. Here there's no transformation, it's the pure definition. Since this process is similar to the covariant, I call this as a delta prime alpha, which is equal to del over del x prime alpha. Then I am saying that forget the transformation or anything, say instead of prime and unprime. So this is very useful. Why it is useful? What are the elements of this when the index is up? Elements of this are positive. So what is the open form of this? What is the open form of this? This is equal to del over del x0. And what are the other components? When x0 is, this is equivalent to what? Or not equivalent, yes, equivalent to what? When alpha is 0, del x0. When alpha is 1, is it positive or negative? Positive, because here, that is up. Okay, so this is covariant, but the components are positive. That is very important. Because of this, we can define that the continuity equation and 4-dimensional Laplace equation in the covariant form. So we call this as a, in that form, positive, del over del x, del over del y, del over del z. So how you can make the indices up? How you can make the indices up? So let me leave the free index as a alpha, and let's say this is alpha. How can I make the indices up? I have to use again the metric tensor. So what is the metric tensor? G, which one? So here there's something wrong. So this should be beta go to the alpha. How it go to the alpha? In that form of the process. So if you contract this beta and beta, you will left out with alpha. Do you agree? Okay. But what happens when I take this in the covariant, make as a contravariant? What is the change in the process? Time coordinate doesn't affect it. Space coordinate goes to the minus of this. So that is equivalent to del of alpha is equivalent to what? That is equivalent to del of x0 minus a gradient. So the next thing I will show you that why this is very important. Maybe you saw already. Maybe you saw already, I don't know. Index is down is covariant, but the space is positive. Index is up, contravariate, but the space part is negative. What is the actual definition? Prior to this, index is up, this is positive, index is down, that is negative. So what happened if I take that the divergence in 4 dimensions? So dimension is 4 dimension will be the continuity equation. And that will help us to define that the covariant form of the continuity equation. So that is very simple presentation. Del alpha A alpha, or vice versa. So when the index is up, that is equivalent to del x0 minus gradient. When the index is down, covariant here. What is this? A0 again minus A. So what is the result of this 4-dimensional divergence? This will be act this one, this will be act this one, but minus minus plus. Therefore, continuity equation will be covariant. So that is coming of this process. This is very important. So this is equal to del A0 over del x0, that is Ct, plus divergence of A. For example, I will define that the 4-dimensional current density, and I will write that the continuity equation. The middle sign will be a positive, and this is covariant. So this form is valid in all inertial frames. This is the property. And the other one, for example, we will define the 4-dimensional, 4 potential. 0 will be the scalar, the other will be the vector potential. That will be the Lorentz condition in that case. So we will do this very, very quickly next time. And another thing, we can define a 4-dimensional Laplacian operator. Four-dimensional Laplacian operator. So basically this is defined as simply del alpha, del alpha. So what is the del alpha when the index is down? Again, it is equal to del x0 plus gradient. When the index is up, when the index is down, up, what is this? Del x0 minus gradient. Okay? Down is positive, up is negative. So if you apply this process, you will obtain del square over del x0 square minus Laplacian. So this is the 4-dimensional Laplacian operator. Actually, this will give us to the, this is covariant as a form, all frames. So this will give us to the wave equations. Okay. Okay, because that will be del square over del t square minus Laplacian. So we will construct the wave equations in what covariant form. So basically the metric tensor and the covariant forms of the contravariant forms of the vectors and the derivative operators eventually help us to define that the covariant form of the tools of the electrodynamics. Okay, so we set up the mathematical structure. So next time, maybe in 2 hours, we will easily write all electrodynamics equations, Maxwell's equations, and what else? Continuity equations and wave equations, Lorentz conditions in the covariant form. Okay, so that's all for today.